Okay, so this is just a single slide set that just has a single proof of that a language, a particular language, is not context-free, using the pumping lemma for context-free languages. On the class website, you can find a document that has this proof written out really beautifully. The slides here, sometimes I'm writing all over the slides and making notes to try and walk you through how this works. So do, after you've watched this, or in fact even better, print that out first, then watch this. So just as a reminder where we're coming from, here's the pumping lemma for regular languages. And remember, when we were using the pumping lemma for regular languages, again, we were using this lemma. This is something that tells us something that is true about all regular languages. These facts are true about all regular languages. So if we find a language that we think is regular, but something in here is not true, then obviously the language we had was not regular. And the idea is that if we pick an infinite regular language, we can take any string in that language that is at least m characters long, split that string into x, y, and z so that the middle part y is not the empty string, and that the xy part, the first part of that, is the length of that is less than or equal to m, and then we can take it, and we happen to know that every other string of the form xyz where we take multiple copies of that y, so xy to the kz, is still in my language. So this was the pumping lemma for regular languages. And the pumping lemma for context-free languages is very similar. You can see I kind of crossed out stuff in here for the regular languages and wrote the equivalent statement for context-free languages. You know, we used XYZ for the for regular languages. Here we use UVWXY. Not sure why we changed letters, but I'm trying to stick with the text. Here it is again, same as the previous slide. I just got rid of the crossouts and said, you know, let's suppose we have an infinite context-free language. Of course, if our language is finite, it is definitely going to be context-free, right? And then if it's infinite, then there is some number m, so that if we have any string in my language where the length of my string exceeds that number m or is the same as, we can split my string into this UVWXY so that these things are true. And the important thing to note here is we're kind of pumping two pieces now, right? We're taking the v part to the k power and also the x part to the k power. So we're doing k copies of v and k copies of x. And as you can think about this, that with our context-free languages, you know, we have things like this. This is a language that is context-free. A, b to the n, c, d, d, e to the n, f, g, such that n is in the natural numbers. And you can get a feel for you know, what can happen here if we pick a string that is where the length of s is at least m characters long. So I mean, maybe we pick the string a, b to the m now, c, d, d, e to the m, f, g, right? These d's are not superscripts, they're just d's. You can imagine that we could take as many copies of that m as we want, or of that b, and as many copies of that e, and pump, as long as we're taking 2 copies of this and 2 copies of this, or 4 copies of this and 4 copies of this, our string is still going to be in our language, right? And the magic of the context-free languages is we can kind of match these things up a little bit, right? With our regular languages, you had to be able to pump just one thing. Now we've got 2 things that we can kind of pump simultaneously, which gives us a little bit more power to keep a language legal. Okay? So here's what I call my plug and chug outline of a proof that a language isn't context-free using the pumping lemma for context-free languages. This is kind of a fill in the blank. So let me show you the outline I'm going to use, and then I will do a proof that uses this outline. And the best way to get full credit on my assignments and on my exams is to just follow this outline, right? So, statement I want to prove, and then you fill in whatever the language is that you want to prove, right? And then you write proof. Let L equal, just write the language again. Assume L is context free. We're going to do a proof by contradiction. So we start by assuming L is context free. We come up with a contradiction at the end, which means that our assumption must be false, right? Assume L is context free. Let M be the number from the pumping lemma. Then we have to pick a string. We got to pick a clever string. You know, now you actually have to do some work and pick a good string. And you need to make sure that that string is both in your language and its length is at least m characters long. Because if it is, then, you know, we can split it into u, v, w, x, y, and all these things apply. Then comes the meat of your proof, where you say something interesting about the v part or the x part, or maybe both. And so then you say by the pumping lemma for context-free languages, and say something interesting about what happens in here. And the idea is that you're looking for a contradiction, because once you've got a contradiction, you know, you prove that, you know, 1 equals 2. You prove that a string has both 5 and 6 letter A's at the same time. Whatever it is, you end up with your contradiction. And then you can say, thus our assumption must not be true. Thus L must not be a context-free language, QED. So this is our outline of a pumping lemma proof. It's not a pumping lemma proof. It is a proof that a particular language is not context-free, and it uses the pumping lemma for context-free languages, right? So now let's look at an example of me using this outline. So let's suppose that I want to prove that this language here, a to the n, b to the n, c to the n, such that n is greater than or equal to 0, in other words, n is a natural number, is not a context-free language. So the first step is we're going to have to fill in the language here. And that was easy. Statement I want to prove. There's my language. I filled it in. Is not a context-free language. Next step, fill in the language again. Starts out easy, and at least in my class, partial credit for doing some of this stuff, right? Okay, so here's what I want to prove, and now I'm going to do my proof. Let's let L equal this. Assume L is context-free. Let M be the number from the pumping lemma. Now we've got to pick some clever string. And a lot of the time, it's convenient to say, well, what if I take kind of the outline for my language and replace all the n's with m's? So now, you know, I mean, keep in mind, this is a language, right? It's a set of strings. This is just a single string. But I'm going to try the string where m is the number from the pumping lemma for context-free languages, and I have a string that has MAs followed by MBs followed by MCs. Okay? And all of this stuff here is plug and chug. It's all the kind of standard stuff that we just want to write every single time. We know this, we know this. This is just stating facts about the pumping lemma for context-free languages. So now we need to go on to the meat of our proof, right? We need to say something interesting about the structure of V or X here. Remember before we were doing it about Y when we were pumping just one piece, but now we're potentially pumping the V and the X. Well, in fact, we are pumping the V and the X, right, simultaneously. So we may need to say something interesting about the structure of V. We may need to say something about the structure of X, or maybe both, and try and come up with why that can't work. So here we go. I'm running out of space, so I've just got this. This is my outline, right? I'm just doing the second half of this thing where I got to do this cool stuff. I just wanted to show you it on a slide with just the right side of the proof from before. Presume we've already written the first part of the proof, and let's keep going. And here's just kind of the key facts from the pumping lemma that we're going to be using. This is not part of the proof. I just popped up this little box here so that you can keep in mind how does it work when we have a pumping lemma proof. Sorry, a proof that uses the pumping lemma for context-free languages. You know, we've picked our string, which means that it can be split into UVWXY because our string is long enough where V and X squished together, the length of that is greater than or equal to 1, so either V or X or both is not lambda, and the length of this whole piece is less than or equal to M, and the string can be pumped. So I just put this up here to remind you it's not part of the proof, but these are the facts we're probably going to be using. So here's what I've got in my proof so far, and I'm going to kind of break it down. I can tell you for sure either V doesn't equal lambda, or X doesn't equal lambda, or maybe both of them don't equal lambda. How do I know that? Because I know that when I squish them together, the length is greater than or equal to 1. So at least one of them is not lambda. And so I'm going to do my proof. I'm going to say, well, suppose V isn't lambda, and suppose V is lambda, right? So it could be one or the other, right? Because if it's not lambda, we don't care whether X is, and if it is lambda, then X is not going to be lambda. We're just going to do a proof. We're going to do some what happens in that case, what happens in that case. Of course, you know the punchline, no matter what we do, we're going to have a problem. But we haven't said that yet. So let's build this up. So if we just do the part where we suppose that V is not empty, right, V is not lambda, then what could V look like? It could be just one letter, right? So it could be just A's or just B's or just C's, right? Because remember, my string is A to the M, B to the M, C to the M. So what could the V part look like, right? The UVXYW, right? It could be just A's, just B's, or just C's, right? If it's just one letter. Or maybe V takes the form where it's two letters, so it's just some A's and B's, or just some B's and C's, right? It can't be A's and C's because it would have to have the B's in there too. Or maybe it has all three letters in it, right? So it's got some A's and some B's and some C's. So I'm just trying to kind of logically say, what are all the possibilities if V is not lambda? Let's keep going. Okay, and let's look at each subcase. If V is just one letter, so all A's or all B's or all C's, then if we looked at this string, right, we know that S is U, V, W, X, Y, and that S is in my language. But if we look at U, V squared, W, X squared, Y, where we have 2 copies of V and 2 copies of X, if you think about that, if we just have one letter inside of V, we're going to end up with more copies of that one letter than the other letters, right, in my string. So if I have just A's and V, then when I make 2 copies of that, I'm going to add some extra A's, but not some extra B's or C's. Now there's one extra possibility in here that I didn't really think about until I started writing the proof out formally. And you'll see it in the slides. If you download the PowerPoint slides for this lecture, you'll see the correction in the slides. But having recorded most of this lecture already, I'm not going to re-record it. I'll just show you. The other option is it is possible that the other letters could be in X, right? So suppose that, you know, V had a couple of A's in it. If X has a couple of B's and a couple of C's, we could conceivably imagine, you know, then this U, V squared, W, X squared, Y would have the same number of A's and B's. But then we have a different problem, right? Then the problem is that the X squared part, we have B, B, C, C, B, B, C, C. The B's and C's are out of order, right? Because our language has all the A's first, then the B's, then the C's, right? And so this X squared part of this U, V squared, W, X squared, Y wouldn't work. It would mess up, and our string would no longer be, would still not be in the language. So in the future slides, you're not going to see, in the future slides in this lecture, the online lecture, it's just going to include this stuff right here, the stuff that's in red. You need to remember that that's not the only case. There's also this possible case that I just described to you. And the case that I just described to you is available on the class website as in the full proof that I told you at the beginning of the lecture. I made available for you. So it just means in future slides, this one little bit may not look exactly right. So when you go on to the next set of slides, you know, when I switch slides in 10 seconds, you will notice that this piece turns black, and it stays the same. It doesn't have this extra stuff, right? But the slides that you download have the extra stuff. Get it? You got it. All right, cool. Thank you. So just to wrap up this slide, where are we? We've decided that V, whatever V looks like, it doesn't contain just one letter, right? So this case doesn't work, but that's fine because there's lots of other possibilities for V, right? V could have exactly two different letters. It could have all three letters, or it might even equal lambda. So we're not done yet. We don't have a contradiction yet. So let's keep going. Well, guess what? If V is just one letter, doesn't work. If V is two letters, then we'd have some letters in the wrong order, right? Because when we have, if V is two letters, let's suppose V is AABB, then V squared, two copies of it, is going to be AABB, and then another copy, AABB. And now my string isn't in my language because it's not of the form A to the N, B to the N, C to the N, where all the A's come first, then all the B's, and then all the C's, because there's some mix-up here, right? We've got some A's, some B's, some more A's, and some B's. So if it's exactly two letters, then this string, after I pump it, would have some of the letters in the wrong order, so it's not in L. Okay, so we've said if V is not the empty string, then we know it's not just one letter, and we know it's not exactly two letters, so let's just see what happens if we say, okay, maybe it's three letters. And you see where we're going here, right? If it has all three letters, some A's, some B's, and some C's, then again we're out of order when we have two copies of this piece V, right? Just like in here, some stuff is out of order. It's no longer of the form A to the N, B to the N, C to the N, right? So what have we shown? We've shown that V can't contain just one letter, right? If we assume that V isn't empty, it cannot contain one letter, cannot contain exactly two letters, it can't contain all three symbols, right? So that's the only possibilities, right, if V isn't lambda. So that's okay, though. We still haven't tried everything, right? We've said suppose V isn't lambda. Well, it doesn't work if V isn't lambda, so maybe we just have to assume that V is lambda. So we know whatever we do, I shouldn't really say S here, right? I should say U V squared W X squared Y is not in my language if V doesn't equal lambda. So I suppose V has to equal lambda, right? In order to be able to do anything with this proof, it's going to have to be lambda, because if it's not lambda, we know for sure that this string here, right, uv squared wx squared y, is not in my language, and it has to be by the pumping lemma for context-free languages. Okay, so here, let's fix this again. That should be u v squared wx squared y is not in L. So now let's just suppose that V is the same as lambda. And if V is lambda, then we know one thing for sure, which is X can't be lambda, right? They both can't be lambda because the length of the concatenation of the two is greater than or equal to 1. So let's keep going, and I just shrunk this down so we can keep going with our proof so you can see what I'm doing. And of course, that should not say S is not in the language, it should say uv to the k, wx to the k, y is not in the language if V isn't lambda. So we're going to suppose that V is lambda. And if V is lambda, then X isn't lambda. And guess what? We have exactly the same proof again. Just pause this and look at it. But what could X be? X could be just one letter, but then same reason why V couldn't be just one letter. Or X could be exactly two letters, but same reason why V couldn't be two letters. Or X could be all three letters, but same reasons again. So where are we, right? We've said that V could be lambda, but of course It can't, because then x wouldn't be lambda and we'd have all this stuff. It still wouldn't work. So here's where we are in our proof outline, right? We've been saying interesting things about the structure of v and x and what happens when you pump your string, right? So now we just need to wrap up. In summary, no matter what form v takes, whatever v is, this string is not in my language. But by the pumping lemma for context-free languages, that string must be in my language. Boy, sorry about these slides. uv to the, 2 copies of v, wx, 2 copies of xy, must be in my language, right? That's a contradiction. Thus, our initial assumption must not be true. What was our initial assumption? Our initial assumption was that L was context-free. We're doing a proof by contradiction. We got our contradiction. Initial assumption must not be true. Thus, L must not be a context-free language. QED. And there you have it. We did our proof. Now, if you want to actually see this proof all written out, you're going to have to kind of go through the video and write it out, because I couldn't fit everything on one slide. But hopefully you get the idea. It's just like the pumping lemma for regular languages. Very, very similar, just a little bit more complicated. And that is, of course, why we spent so much time on regular languages. We wanted to start with the regular languages. If this is too confusing for you, please, please, I beg of you, go back, look at the proofs for pumping lemma, the proofs that languages are not regular that make use of the pumping lemma for regular languages. Okay? All right. Get ready. The next lecture is going to be super fun.